Okay, so our conversation with chemistry really begins with this chapter. Chapter one was about the scientific method and what chemistry actually is as a science, but it doesn't really get into any of the details. Chapter two is about measurements and numbers and all of the math associated with chemistry. And so now we're going to finally break into actual chemistry. So remember, chemistry is the study of matter and the transformation it undergoes. So in order to understand chemistry, we need to understand matter first and foremost. So matter is anything that has a mass, anything that has mass and takes up space. So those are the two requirements that are needed to make something matter. We generally avoid something like a photon, like a burst of energy from light. That doesn't really count as matter because it doesn't take up space, although it does have a small mass. Okay, so matter is broken into three different phases. These are solid, liquid, and gas, and they all kind of have their own unique properties associated with them. And we're going to talk about plasma in just a second, but solid and liquid and gas are a great place to start. So a solid piece of matter, again, if you were to take a sugar cube, for example, it has mass and it does take up space, much like a liquid or a gas would as well. Gases are a little bit harder. There is a kind of a division between gases, liquids, and solids, but generally, these are the three phases of matter that we are interested in. The fourth state of matter is plasma, but we're going to talk about that in just a little bit. So a solid, some characteristics about a solid. A solid is typically going to have a definite volume and shape. Okay, so you look at this piece of solid here, this cube, and it has a volume and a shape. You can see those two things. It is really, they are all very close together. Okay, so this is a piece of solid. You notice that these things are connected to each other. They're neighbors. Each one of those particles has a neighbor. Okay, so solids are just kind of firmly everything in its place. They always have the neighbor. There's no movement at all, really. They're just stuck together. So that's a solid. Definite volume, definite shape, and generally just kind of a solid, exactly what you would expect. Next up, we have a liquid. So a liquid does have a defined volume, but that volume, it does have a defined volume because we have measured them in lab, right? You have measured milliliters and those types of things. So it does have a defined volume. But the shape, on the other hand, actually the shape of the container. So it takes the shape of its container. You'll notice this liquid here in this flask has kind of settled to the bottom. If we put it in a Petri dish or we put it in a graduated cylinder, a really tall thing, it would take the shape of whatever container it's in. And liquids are a little bit different because they can kind of shift and move around. They're still touching one another, as you can see here, but they're allowed to like change partners, right? This thing is going to work its way over here and start to interact with this one. These are going to move over here. So they're just kind of, they're shinning around and shifting. And you can see that because you can mix a liquid and all of those particles kind of mix together. So a liquid is a defined shape or defined volume because we can define it. And it has the shape of its container. And then finally, gas. Gas is a little bit different, and we're not really going to get too in detail with gases, but gases take the volume of their container and no defined shape. So there's no defined shape, but they take the volume of their container. So if I had one particle of gas in here, it's going to fill the whole thing out. And generally what happens is gas particles are going to move and they're just going to kind of bounce off walls. They're going to bounce off each other and they're just going to be moving at a really rapid pace. Gas particles are constantly moving, and that's really what we see. These things are constantly moving. Notice that there is zero interaction. There's no interaction between these things. They don't interact at all. They're just moving really fast. They're bouncing off each other, right? This might bounce off another one, but ultimately they're never going to interact. So they don't really interact at all. They're just kind of moving all over the place. The only other thing that I would mention about gases is they are compressible. I can take these things and I can start to turn up the pressure, put them in a smaller and smaller container, and I can force them closer and closer together, right? Compressed gases are just gases that are kind of defined to a small area. So pressure becomes important. So pressure is important, but we don't really have to worry about that right now. I just recognize that the three different phases of matter, liquid, solid, liquid, and gas, the shape and the volume are kind of their defining features for right now. The fourth state of matter is something called plasma, and we can see it up here. Plasma is kind of these charged particles. The aurora borealis is what happens when particles in the air get charged by the radiation from the sun. And when you burn a flame, it's charged particles. So plasma is the fourth state of matter. It doesn't really count, but it is technically the fourth state of matter. But we're going to focus on solid, liquid, and gases. We're going to leave plasma here and not really worry about it anymore. Okay, so when we talk about matter, we have to recognize that there are certain things that nature tells us is going to happen, and they're always going to behave. Law of conservation of mass is one of these things, and it's really pretty straightforward. Matter cannot be created or destroyed. It can only be converted into other forms or other substances. Okay, so ultimately what we see is if I start with X amount of matter, I'm going to end up with X amount of matter at the end. So when we start a reaction, we always have the same at the end as we do at the beginning. So our examples here is I have pre-beer is typically basically just some water with a bunch of sugars in it. And you add some yeast, and that yeast turns all of this sugar into I should say all of this sugar gets turned into ethanol or gets turned into other things. The sugar molecules have transformed into something else, into ethanol, but there is still the same amount of material, same number of carbon atoms, same number of oxygen atoms and hydrogen atoms that we start and we end with. So you're always going to end up in a state where you have the same amount of matter that you began with and when you start with. So what we typically say is when we run a reaction, the matter before equals the matter after. Okay, so we always end up with the same amount of matter, but it's just in a different form. It just changes what it is, right? We go from sugar to ethanol, right? The example that we have below is I have a sugar molecule turning into ethanol, right? So that's pretty much it. Sugar turns into ethanol, but we have the same amount of everything that we have present. Another example is a battery. Okay, so this is a little bit more intense in terms of its complexity, but the idea here is a battery starts in a state and it gets rid of electricity. And so it starts with lead and lead oxide and it turns into lead sulfate. But I have the same mass. The battery does not gain or lose weight. Always starts with the same weight and ends with the same weight at the end. Okay, so we always start with the same mass. Again, start with the same mass and end with the same mass. So the matter is not created nor destroyed. We have the same matter all along the way. So atoms and molecules. So we're going to talk about atoms. We're going to use these terms. Atom comes from the Greek atmos, which basically means indivisible. Okay, so an atom cannot be divided. So if I have a small atom, it is going to be that same atom for the rest of its for eternity. Okay, so here I have some gold. Okay, and here I have some sulfur. These atoms of gold, which is the atomic symbol Au, we'll get to that in a little bit, that will remain Au for eternity. And sulfur, a sulfur atom will remain as that ball of sulfur, just remain that single sulfur for eternity. We have some really interesting ways to see these things. This is actually, I believe this is silver, Ag, but each of these little spheres is a silver atom. So we are capable of actually seeing these things with some pretty neat photography. So an atom, just simply recognize that an atom is one of these spheres. It's this indivisible type of particle that we're going to start to look at. Okay. Now, we have atoms which are all of the things that you see on the periodic table. So carbon, hydrogen, oxygen, nitrogen. I don't know. We have some here, sulfur, gold, so on and so forth. Each of these is considered an atom. It's an individual thing. But when we put those together, we start to build, and actually, if we look all the way over at E to start, this right here is an oxygen atom, this is a hydrogen, and this is a carbon. This thing right here is a particle of this fiber of cotton. Okay, so this is what we would see with our naked eye. Okay, so this is a cotton ball or boll, as we would say. That's directly off of the branch. And if we zoom in at 40x magnification, this is what an individual one of those pieces of that cotton ball looks like. And if we zoom in even more with an electron microscope, that individual part is made up of a bunch of all smaller fibers. So this is an electron microscope. Can see even smaller. And then we can start to see these. This is an X-ray. We can use X-rays to see even smaller than that. And so we can see the individual atoms. And so this right here is just one molecule, but you notice 1, 2, 3, 4, and so on. And each of those strands is composed of one of those, of a bunch of those different cotton molecules. Okay, so cellulose type molecules. So what I'm saying is the world is very small, and we can use these little methods to see them. But the cotton ball at A there breaks down into an individual molecule, and each of these individual molecules. So this whole thing is a molecule composed of individual atoms or a group of different atoms. And so we're going to talk about that next. Okay. All right. We have to recognize that this right here is a bunch of different molecules. So if you have more than one atom, I'm going to call this a molecule. This is a molecule. All of these, if you see this little subscript here, it indicates that all of these things are molecules. Okay, so all of these things contain different numbers of different amounts of things. So we have hydrogen all the way on the left, H2. It's just simply two hydrogens hanging out together. Oxygen, we've got two oxygen atoms that are bound together. They're holding on to each other. Phosphorus actually comes as P4. So we have 4 phosphorus atoms on these little balls is what we're talking about together. This is sulfur. Each one of these little balls is sulfur. And so we've got a bunch of these. Okay. Water, something we should know well. So we'll notice right here, these are just, we're going to call these elements, or what we should simply say is only one element, right? Each of these only has one element present. The first one is hydrogen, second one is oxygen, next one is phosphorus, and the last one's sulfur. But they would all be considered molecules because they're not just one individual, okay? And we'll get into the specifics of this. But the rest of these are molecules as well, but they contain more than one. So this is oxygen, and I have 2 hydrogens attached. So now we have some combination that is not just one type of atom. Right, here's the carbon in the center and oxygen on either side. And a more complicated one, the one on the far right here, is glucose, C6H12O6. It contains the same amount of carbon, hydrogen, and oxygen. All of these are considered molecules. These are not elements, okay? We actually call these compounds because they have more than one element, or 2+ elements. So these are elements over here. And we recognize because they just have one type of atom. Compounds, elements. If you have one type of atom, or I'm sorry, yeah, one type of atom, phosphorus, sulfur, oxygen, gold, whatever, it's going to be called an element, just pure element, okay? Can still have a bunch of them together, like 8 sulfurs or 4 phosphorus, but still considered an element because it's only one thing present. Okay, we're going to see this in just a moment even better. Compounds, however, contain more than one. If I have hydrogen and oxygen together, we're going to call those things compounds. Okay, so it's just a set number of things. And so once we get down to matter, we're going to start classifying matter. Okay, so matter is the overarching thing is the matter. So matter is, again, anything that has volume or has mass and takes up space. Matter is going to be broken into two different categories. We're going to have what we call pure substances. Okay, a pure substance is something that is, well, it's pure. It contains, pure substance is going to be only one type of thing. It's going to be all sugar or all water or, all gold or something like that. Pure substance is just one substance and that's it. Versus a mixture, which might be more than one thing. So a mixture will be more than one thing, I should say. So a pure substance would be something like water. So an example we would use is water is an example of a pure substance. But a mixture, an example of a mixture might be salt water. Salt water is essentially salt and water combined into one. Okay, so that would be, it's two things mixed. Okay, so pure substances can then be further broken down. So if I take my pure substances here and I break them down further, there are two options for pure substances. We can have elements. An element, again, by definition, is only one atom type, I should say, because we can have more than one. Like I said, O2 is, oxygen, but it's only one atom type. It's only oxygen. And the other type of pure substance is what we're going to call compounds, which we looked at above as well. Compounds is going to be more than one atom type or element, I should say. But always a fixed ratio. And I think we'll discuss that in just a second. Yeah, actually, I will discuss that in just a moment. Always a fixed ratio. Okay. All right. So let's kind of take a moment and let's break it down a little bit more. So let's take a look at elements as a whole. So elements, the elements that we're going to talk about. So elements would be something like, okay, if I have, which is gold, that is an element because it's the only thing present. But O2, which is oxygen gas, it's still only oxygen present, okay? And so we're going to get into the periodic table, and it's going to be important to have one on you. And I'm going to post one very soon, or there is one on our on Brightspace that you guys are going to use for the final and every other test as well. But oxygen is on there, and it comes as O2, okay? Something like sulfur. Sulfur comes as S8. That's still just sulfur. So we're going to count that. No E. Sulfur, there we go. But that is going to count as an element as well, because the only thing present is sulfur. But compounds are a little bit different. Okay, so compounds come in the form of having a fixed ratio. What is water? Water contains H2O. Okay, so two hydrogens and one oxygen. So what we're seeing when we take a look at something like this, two oxygens, that means there are two hydrogen. And if there is no number, that means one oxygen. Okay, so two hydrogen, one oxygen. Every single water, no matter where you are, whether here, if you're on Mars, if you're in China, doesn't really matter, is always going to be the same, two hydrogens to every oxygen, H2O. Okay, and in fact, if you need more, so if I changed it very simply, H2O2, now it's two hydrogens for every two oxygens. This is now called peroxide. Okay, so this is a compound because it's fixed, two hydrogens, two oxygens, but now it has completely changed what it is. So this was water. This is now peroxide, the stuff that you would use on a cut, okay? So just adding one oxygen to that compound completely changes what it is, okay? Peroxide can be explosive in pure form. Water is completely inert and it's totally fine. Peroxide you would never drink. Water you drink to sustain life. So any small variation can change what a compound is. But in the end of the day, a compound is always going to be a fixed ratio. Okay, so you're always going to have the same thing. As soon as you change it, you've changed what it is. Okay, and the last example that I'm going to use quite a bit is sugar, which is C6H12O6. So C6H12O6, glucose. Okay, so here I have 6 carbons, 12 hydrogens, and 6 oxygens for every single glucose molecule. Okay, so those things are considered molecules. Okay. Okay, good. So compounds and elements make up a pure substance, and we identify those things as that it's the only thing present. Okay. Next up, we take a look at mixtures. So a mixture is actually just very easily defined as one, or I should say, 2 or more pure substances. So the example that I have above, salt, which is sodium chloride, it's the table salt, for example, and water, H2O. Those two things are combined together. They're around one another. Salt and water count as a mixture, 2 or more pure substances together. Sodium chloride is a compound. Water is a compound because they're both fixed, right? 1 sodium, 1 chloride, 2 hydrogens, 1 oxygen for water. So they're both fixed in what they are, so they would be considered compounds. Okay. We can also have a mixture that contains an element. Okay, so you can take hydrogen gas and you can dissolve it. Weirdly enough, as you can dissolve it in air, right? Nitrogen and hydrogen together are both elements, but if they're combined together in a mixture, if those two things are present together in the same container, that would be considered a mixture. So mixture comes in 2 different forms. Again, what we need are 2 or more pure substances. Mixtures come in 2 different forms: homogeneous or homogeneous, a homogeneous mixture, or a heterogeneous mixture. I'm going to rewrite that because my writing is terrible. Or heterogeneous mixture. Okay, a homogeneous mixture is it is going to be uniform throughout. Okay, so what you see is if I look at this coffee here, this sample down here is the same as the one up there. Those two are the same exact amount of different types of compounds. This sample right here is the same as all of those. So it's uniform throughout. It's visually, and that's the other part of it, uniform throughout or visually indistinguishable. So every single portion of that is essentially going to be the same. If you took a sip of coffee, they're all going to taste the same, okay? But this here, this piece here, this mixture of vinegar and oil, so oil on the top, vinegar on the bottom. This is a heterogeneous mixture. It's visually distinguishable, right? I have oil. If I took a sip from the bottom versus a sip from the top, I would get oil on the top and vinegar on the bottom. Okay, so if I took a sample of this after I gave it a little bit of time to settle, or versus a sample like this, not the same as this. Okay. So every single different, that's if I shook the bottle, right? So those things will look almost visually distinguishable, but you can clearly see in here that there are pockets of oil versus pockets of vinegar. Okay, so it is visually distinguishable. We can recognize the difference between the oil and the vinegar and such. Okay, so those are the 3 different types of, 4 different types of matter that we have. So pure substances, elements and compounds, mixtures, heterogeneous and homogeneous. And we're going to talk about separating these things in the last little bit, as I'll say, you can take a mixture and you can divide it into pure substances by physical means, by physical changes. Okay. Really simple. We're going to do this in lab, but if I wanted to remove salt from water, I can just evaporate the salt. I'm going to have the salt left and the water will have evaporated. Okay. But I cannot do the same thing going from compound to an element. I have to do chemical change. Okay. So if I want to separate water into its two components, hydrogen and oxygen, I actually have to add electricity to it, and it's going to separate it into hydrogen and oxygen. Okay, so it's going to be through chemical means. We're going to destroy the things, and we're going to talk a little bit more about that as well. But this is kind of the overall kind of hierarchy of matter. Okay, so classify the following as pure substances, homogeneous, or heterogeneous mixtures. And in fact, if it's a pure substance, please tell me whether it's an element or a compound. Okay, all right. And so we are going to do this example in class. Do your best to determine what something is. So again, I'm going to go over these if you need to take little notes here. An element is only one element. A compound is one or more than two plus, I should say, two or more elements present. And they have to be at a fixed ratio. A homogeneous mixture is two or more pure substances. And those pure substances would be an element or a compound, can be either. Okay. And then homogeneous versus heterogeneous, both those mixtures are the same definition, two or more pure substances. But remember, homogeneous is uniform throughout, and heterogeneous is you could see the differences. And so we're going to talk about this in class. We'll talk about these in class. All right. Classify the following as element, compound, homogeneous, or heterogeneous. So imagine if this is the container, okay? Element, compound, or what type of mixture. And on top of that, I also want to know what physical state, solid, liquid, gas. So which one of those is present, or more than one? Do you have solid and liquid, or liquid and gas? Okay. All right. So yeah, we'll take a look at this together as well. All right. So that's good for part one to understand physical and chemical. So basically what we're looking at are the different types of matter that we have. And this is really the crux of all of this. You need to kind of understand these things. Again, elements, compounds, homogeneous and heterogeneous mixtures, they're going to kind of become second nature after a time, but this is a really important thing to understand. Okay, so that's the first part. That's section one.